Switch to YouTube. Okay. Yes. Yeah, I will try to check the chat in Telegram, but it's a bit harder. So, yeah, it's better if you go on Zoom. Okay, so this lecture, it's optional material, so you don't need it for exam. But in the seminar, it's useful for, there is an exercise. There are 3 exercises, but they are colloquium questions, but you already understood from Telegram message. And there is also a sample exam. And there are 2 exercises that fit the materials of previous lecture, and also a little bit this lecture. So I don't know, it's too much for one seminar, so you can maybe push a little bit if you have certain choice for exercises. Okay, and so this lecture is very nice. So for theoretical computer science, I hope so, because Artyom asked about lower bounds. At least he finds it nice, as he clearly indicated last time. Yeah,
it was nice when we were kind of talking about streaming algorithms. So I'm not sure that it will be nice now, but we will see.
Yeah. So no positive results today. So you can decide whether you like it or not. So we've seen this algorithms for F0, and then I didn't explain F2, but actually you know enough. Like you just need, if you know one little trick extra, then you know all the trick to understand F2 characteristic. So since F infinity is too expensive, people compute F2 to understand whether there is a very frequent element. If there is a very frequent element, F2 will be a bit higher. Okay. So, and our algorithm, so if we fix the error probability, they run in time 1 over epsilon squared log mn. And we had 2 approximation algorithms that were probabilistic. So then there are a bunch of questions, like, can we do better? Because when sometimes algorithm is used in unexpected contents, and maybe you think about Facebook applications. I don't care whether I know the approximation of number of views of a message up to a factor 3. I don't care about this. But there might be another approximation of F0 where you want to have 1% accuracy, for example. And so this dependency on 1 over epsilon squared is painful because it's factor 10,000. So in Facebook, there is whatever 100 billion messages. If you need to pay 10,000 factor extra for each message, it means a lot of logistics to store everything. And so can we have 1 over epsilon? This is an example of a question. We also had probabilistic algorithms. Can we turn them to deterministic algorithms? Is there any chance in the extreme version of reducing epsilon, can we have exact algorithm? And so all these answers are no. So the 2 algorithms, well, the algorithm for F0 we've seen is the best possible.
Are we talking about the algorithm with a random hash function?
Yeah, with random hash function, and we remember the smallest value, and then we invert. It's the best we can do. And so, but actually, for probabilistic algorithms, we said last time that we cannot have exact algorithms, and there we use the result from one-shot communication complexity. For exact deterministic algorithms, we already understood that we cannot have good algorithms unless the memory is linear in the number of items or the number of, so the minimum of length of stream and number of different items. So this we already understood. We cannot have exact and deterministic. And the proof was kind of easy. So we understood, we run the streaming algorithm. And then before we get the last element, we send our memory to somebody else, and he can then try all last elements and basically reconstruct our set when we're talking about F0 characteristic. And that means we just have to store all information about the sequence in our memory in order to compute F0 deterministically and exactly. And then I announced the result that actually the same is true for probabilistic communication complexity, one-shot communication complexity. And for this, we understood that exact answers with probabilistic streaming algorithms will also require linear memory in the minimum of n and m. It was the same reasoning, except we need to believe this bound for probabilistic one-way communication complexity. So that's what we said last lecture. And today I will give proof that one shot is also a good name, I think. Must be some reason that it's in my memory. So one-way communication complexity of set disjointness. Probabilistic one-way is also linear. So we will start with the bound of this, and then we will move to 1 over epsilon. So we will give a lower bound that depends on 1 over epsilon squared. And for this, we will need a different problem, not set disjointness, but a gap Hamming. I will define this problem and then prove that this, and this actually has kind of unexpected, beautiful proof, this one. Okay, so our first task is this theorem. So let us say that, let us write it in details. Okay, let me repeat what is set disjointness. Oh, I guess I need to repeat what this one-way communication complexity. Yeah, and especially randomized communication complexity. So there is Alice and there is Bob, and so Alice has an input X from a set X, and Bob has an input Y from a set Y. And they want to know the value of a function. So Bob needs to compute a value f of xy. So f is a fixed function, and we're going to define the one-way communication complexity of this function. And it has to happen in one way. That means that Alice will send a message that depends on her input, but does not depend on the input of y. Alice can only see her input. She needs to say something. And then Bob gets the message, and Bob will need to say, let's say there is a function Bob answer, and it depends on the message and the input of Bob. And Bob answer needs to be equal to the function value. So that's the task. This is for deterministic version of one-way communication complexity. And so a protocol is defined by two functions. Functions to generate messages, and Alice function for messages, Bob function for answers. And so the cost of the protocol or the communication of the protocol mx ends is just the maximum over all possible inputs of y doesn't matter here. It's just maximal size. Doesn't matter. This one-shot communication.
Basically, Bob answer is just the function of xy. They should be.
Yeah. Bob answer needs to be equal to this thing. That's what we said last lecture. And we also gave a probabilistic variant. So what is different here is that Alice and Bob also can look to a screen that they can both see, and there a random string is written. So I will define version with public randomness. So there is a general result in communication complexity that public or private randomness is about equally good. So there is a difference in log size of the set X. So with a few bits extra, you can turn public to private random. But I will not speak about this. So this input, so R, there is a set with randomness, and this randomness goes to Alice and Bob. And now Bob answer also depends on this shared randomness, and Alice message also depends on shared randomness. And so the communication cost here.
Yeah, but neither of them can change the R from R. Yeah?
No. They look at the screen and they cannot control the screen. Yeah, that would be cheating. Otherwise, Alice could send X to the screen, and then Bob sees them.
Why doesn't they just send her X?
The idea is that X is very large.
Oh, okay, so in the hash function from X, some. So we need to send some small amount of.
Yeah, indeed. Yeah, you can think hash function, but then what kind of
just function?
Yeah, indeed. M of X is just so.
So we need to compress X.
Yeah. Okay, but here X is, for example, all strings of a given length. So X doesn't contain like interesting structure. So just with hashing, no much progress, because you have no X is kind of trivial. Yeah. I mean, this X is trivial, and this X can be any element.
What does the randomness give us in this case? So just for privacy.
Randomness gives a stronger lower bound. So there are more protocols, and thanks to the randomized lower bound. So now I will prove linear lower bound for randomized protocols of set disjointness, and it gives us a lower bound on memory for randomized exact streaming algorithms. And we used it last lecture. We discussed it last lecture. We just didn't prove it. That one-way communication complexity of set disjointness is flat. Okay, so set disjointness. So the problem is that X in set disjointness. Okay, I don't have any color, so Alice gets a subset. So Alice receives X is a subset of N. So Alice receives a set. Bob receives another set. And f of xy is equal to 1 if x intersect y is empty.
Well, actually, it's not so obvious why it's almost the same, the random and non-random variant of communication complexity, because why Alice can just, for example, she has some substring which she wants to send to Bob. Why can't she just find if there are equal substring on the random string and send just the beginning and the end of substring?
Yeah, but how to encode this beginning in bits? How long will this be for a random string?
Well, it's it's a maximum logarithm of the length of the string.
Okay, so let us say that R, you can think it's infinitely long. We don't care about the length, and then we can apply your trick. But the problem is that to find a segment, a random segment that's by coincidence equal to X, you need exponential length. The index will be exponentially high, so its size will be about the size of X.
Oh, okay.
Yeah,
So it's not useful.
yeah. This unfortunately, there is no magical trick using randomness.
And how is it proven that there is no magical trick? Just the idea.
Well, well, it's not my task to prove that your ID fails. It's your task to prove that to write down the probabilities, and the only bounds you have. So you will look to various events to find the initial segment, and you see that it will be exponentially small in the length of the string.
No, I mean, well, not the proof that my idea fails. You said that it's the same. So what's the idea of the proof that?
No, not for all problems. It is the same.
Not for all.
There are problems where it's different. Okay, it's a long time ago that I've read any book about communication complexity. I forgot everything. I'm ashamed to admit. And equality of two strings with deterministic complex, you cannot do better than send everything. But to do it probabilistically, you can send hash functions, and it's very short. And so there is a huge gap, if I remember correctly. I need to be careful. I keep reading books, but if it's 3 years ago, everything is forgotten. So, but there for sure there are functions with a significant difference between probabilistic and deterministic. Okay.
And both know like a big
Yeah, of course, they know the set X and R and Y, and usually they are strings, but now I say that they are subsets, but basically any subset is also a string of length n.
So we need to try.
No, yeah.
We need to find an intersection and understand if there is.
Yeah. If there is, if intersection is empty, then
I have an idea that is used in the industry. So when we just, for example, calculate hash functions for all the elements that are in our set, and we transmit not the elements or hashes themselves,
Yeah.
but the first 5 bits of the hash, for example, and then if we have intersection, we just check.
yeah. And I will now prove that you can get no more improvement than a constant factor by this.
Yes, of course,
Yeah.
it's the constant factor improvement, but can be something.
Yeah. If a probability, if you're happy with some error probability, then it should be a good technique. But then you get only linear improvement at the cost of constant error probability. Okay, so set disjoint is fine, it is clear now. And so let us write the theorem. Every algorithm for set disjointness. Some people try to enter, but I guess I should not worry about it. Every
They're searching for the actual.
Yeah. Actually, do I need to rewrite? I can just expand this a little bit.
They joined us. It would be interesting for them to listen to the lecture.
Yeah. Okay, let us write it here. I will not be late. So every one-way communication protocol that solves set disjointness for every input.
Well, I'm not talking about the deterministic communication.
Yeah, sorry, every probabilistic uses at least a marker to the then and bits with probability 2/3 uses at least omega n bits of communication.
May I ask a dumb question?
Yes, please.
I just forgot what is omega.
Okay. No
I
problem.
remember what is O big.
Yeah.
What's omega? It's the other side. Other side inequality. Google says that you
Yeah.
have not more. This at least.
Yeah, actually, when I write omega, I don't need to write at least. So, but now I have also at least and then bigger than. So we will have
And
n over
divided
1000.
by 1,000, or we can just put any number here.
Well, it needs to be a fixed constant. I don't know the constant, but I put 1000 just to be okay.
So yes, it sounds like it's enough.
Yeah. No, I think 1/20 should also be enough.
Yeah.
And you're right, for big omega, it only starts from large enough input. But here, I think with 1000, and I round down, so we will start from large enough input.
Mhm.
So big omega means that at least there exists some coefficient, so that if n is large enough, you need at least, so if n is more than this, there exists a coefficient and a constant, so that n is more than this constant, then you use at least.
So can it be
coefficient
proven
times-
that the 1,000 is enough?
Yeah, we will get it from our proof.
Oh, okay.
Yeah. Okay. So, and I will actually prove this theorem for a special case of set disjointness, which is called the index problem. And so here Alice gets a set and Bob gets a number bounded by n. And he needs to say whether this I, so he gets a number I bounded by n, and Bob has to say whether I is an x. One is I and x.
Oh, but
I can write it with indicator function.
the previous question was just the same. We say that we are in code with the elements of the set as by strings.
Yeah, that's why it's called index function, because you can say the input is a string, Bob knows I, and you need to tell the I bit. It's equivalent to A. Actually, it's a good idea to write it like this. It will help us for the proof. So, thank you. Let's listen to the name. So we get X the string, and we can view it as a set. It's the set of all indices for which the string is 1. So 0, 1, 1, 0. You can associate with the set 2, 3. Because 1 and 4 bit are 0.
Ah, okay.
Yeah, you just count, it's very easy. So this is equivalent variant of the problem. So, and then formulation of X is even easier. That's why it's called the index problem. Okay. And this index problem also satisfies the same thing here. It's a special case of set disjointness, because here we can use singleton sets I.
What is really the words?
They're just the indices of the bit coordinates. So first bit, second bit, third bit, fourth
I
bit.
understand, but why they have first 1, 2, 2, 3?
Because second and third bit are 1. So that's how we translate string to set. I'm explaining why
Sure.
why it doesn't matter whether we give Alice a string or a set. Okay. So now let's prove this theorem. But here I will use this index problem. Actually, I forgot how it's called. In rough got its lecture notes. What does it call? Yeah, index problem. Okay. Yes. And our first step, we will transform our problem to a deterministic communication problem. So we will prove. So there's a result from Yayo. And it says that if there exists a deterministic protocol with at least certain length, then there exists sorry, I forgot. Sorry, I always split it. Yeah, let me just read it so that I don't make mistakes. So it says that let's look. So in our objectives, we want to be right with probability. So I didn't say what this criterion to be right for communication protocol. So we want to be right with probability 2/3. So we need that probability over R. So we take our uniform element in R and the probability that both ends of M over X, Y, and R. Okay. Is equal to F of X, Y. Needs to be at least 2/3.
During this course, I've found myself asking a question: why do we take 2/3? Why not?
Yeah.
Is it just a number that we like, or is it based on something?
Yeah, it means that since our theorem it gives just about up to a constant, we can always change the constant.
No,
by repeating a few
this
times.
number is used in some definitions.
Well, we need some number that is more than 1/2
Yes.
in order to boost certain things, but we cannot ask for 1, so we need something in between. And so I take
So it's just a
2/3.
good number, but it could
Yeah.
be some other number.
Yeah. Okay, you can take any number and it will change this constant here, 1,000, but it's not so relevant. And this is just the smallest ratio that satisfies conditions. That's why I use it.
Excuse me, but
Okay. So
Excuse me.
now we will go to our nice proof and prove that index function cannot be solved with less than n over 1,000 bits. And first step is Yayo's theorem. We will move from probabilistic protocol to deterministic protocol. But we will do it with a target where we want to be right. So let me just read the statement because otherwise I will say it wrong. I have trouble to memorize it. So it says that okay, so we will, so what Yayo said, that we will fix the distribution. So fix the distribution D over inputs. So we will construct the distribution D over inputs, and every deterministic protocol will do bet on average over these inputs. We will prove this. And then we will conclude that every probabilistic protocol also uses a lot of communication. So the Yayo's theorem says that if there exists a distribution such that every deterministic protocol fails on average against this distribution, then probabilistic communication complexity is big. Oh, there is someone. So Sorry, my sound was quite soft, so you can speak in the microphone. And let me read your comment. But if we have random string, Alice can just send Bob whether her id bit is the same as the random string and the cost would be 1, wouldn't it? So the thing is, Bob knows the index. So in this thing here, Bob, let me change the scheme for index. So x has a string 0, 1, n, and Bob has this number I bounded by n. So Alice can decide to send her string, but that is n bit of communication. And our goal is to be smaller than linear. So that doesn't help. Of course, if we have two-way communication complexity, then indeed Bob could send this index. So this problem is easy in the standard definition. Okay, good question, because you need to tell what is the real problem.
Yeah, I don't understand. The theorems, we have two theorems now, which we want to prove.
Yeah, well, there is one theorem. This we want to prove that index problem, which I described there, requires linear communication complexity.
That's okay, but what's the theorem of Yao?
Okay, I still need to explain.
It's also a theorem, or it's the beginning of the proof of the first theorem.
Well, it's a theorem. That's the beginning of the proof of this.
Okay.
Yeah.
Okay, so it's lemma.
Yeah, actually, it's called lemma in the literature. Sorry, yeah. Well, you can use theorems in your proof and lemmas in your proof, but no, normally this is called lemma. You're right. It's kind of okay. So fix d over pairs xy, and then if every deterministic protocol, of course, I mean one-way protocol, achieves is doing bad on average over these inputs, is doing good on. So every protocol that's doing good on average over the inputs needs at least k bits of information. Then every probabilistic protocol in this definition also uses k bits, at least k bits of information. So if every deterministic protocol has probability for pairs xy according to d, p is wrong. P is the name of the protocol. Pair xy smaller than 1/3. Then well, uses at least k bits of communication. Use at least k bits of information. Then every probabilistic protocol also uses at least k bits of information. I cannot write it here, so you will need to store it in memory. Is it visible? Let me pin. Okay. So let us check if the statement of theorem is clear. So the assumption is very long. If every deterministic protocol is doing that does well on average over inputs from distribution D, uses a lot of communication, then every protocol in the standards probabilistic scheme is also using a lot of information on average.
So now we are going to prove it's.
Yeah. So we need to prove the lemma, but it's kind of easy. It's one line.
What is written in the brackets? P
is wrong on, I forgot the is. Yeah, P wrong on pair xy for a random y taken from this distribution D.
and X. So we have a random pair.
Yeah, a random pair over D.
We have a deterministic protocol that uses some distribution,
Yeah,
and in average result.
yeah. In average, the result is good. But if each such protocol needs k bits of information, then we achieved our goal. Every probabilistic algorithm also needs k-bit of information. So we will come up with some distribution D and then prove this claim. And then we are done.
Then for all what?
Every probabilistic protocol according to standard, I don't have space, but every probabilistic protocol according to standard also uses at least k bits of communication.
Will we prove that every deterministic protocol requires k?
Yeah. That's our plan. So that's why I write the lemma. But I mean, whoever invented this, whatever. I guess these are the famous. But Yayo invented this theorem, and then some Indian guys, Nissan, Woodruff. I don't know Woodruff.
But why randomized protocols even useful if we use the same lower bound of memory?
Well, be careful. Here we say that we need to prove something stronger. So here we have it has only to be good on average over the inputs. Normally for deterministic protocol, we have to be good on each input. So this is a harder task, and that's why we get stronger lower bound. So here, normally we always think about worst case complexity for each input individually. So this is kind of a strange statement for us. This is the first time we care about average over inputs. Okay. More questions about the statement. Okay, so now let us think how we prove this. And we will prove contrapositive. So we will assume that okay, let's have strict inequalities. Sorry for personal takes notes. So let us assume that we have a probabilistic protocol and with public randomness that uses at most k bits of information. And then we will get a private protocol that uses at most k bits information. So for each distribution, we will get private protocol with at most k bits of information. Okay, so how does it work? Yes, you remember theorem now, right? So I can delete theorem, or I can delete overview. Okay, delete theorem. Yeah, there is a summary here, except that now disjoint is this index function. Okay.
We take probability over x and y and don't take probability over r. Yes, like we fix r.
Yeah, so here is deterministic protocol, and here is no r. But
yes,
here we
yes,
have
yes.
r, and indeed that's all we have to do, fix r. I need to. So let us start with exist contrapositive exist probabilistic protocol with at most k bits of information of communication. Okay, so what it means that for every pair xy, probability over r in the randomness p with randomness r. So that's the protocol when we fix r to be the randomness. So note that if r is fixed, we get the deterministic protocol, right? So we will choose a random r. We just take a random distribution over deterministic protocol. That's what we say. So p run on xy is smaller than 1/3. So we have it for all x and y. Okay, now fix the distribution. And we need to prove something for every distribution. we can get the deterministic protocol. So figure D. And so if this is true for every input, then it's true on average over D. So for all, I will replace by expected value for xy from D. It will still be at most 1 there. Okay. And now we are done. Now we have our now we have our deterministic protocol because we know how to choose R. So how can we choose R? So let us split probability and expected value. You know, from probability course you can do this, right? So we have expected value over R and probability over xy from D, so that P is wrong on xy is smaller than 1. So I just split these two things. And now we can use probabilistic method. Expected value over R of this probability is small. So we know that there is an R for which this probability is small. Now we fix this R. And sorry, I forgot the R here. We fix this R here, and we get deterministic protocol. And the amount of communication is exactly the same as for randomized protocol. Because communication is take a worst case. So if we have worst case, it can only get better, the amount of information. So we have proven lemma of Yao. And actually, lemma is true in both directions. So so if every probabilistic communication protocol needs at least k bits, then you can come up with a distribution that for every deterministic protocol, you use at least k bits of information. And it's proven with minimax theorem. So these probabilities, you can write them as like matrix product. And then these quantifiers is kind of neat, but it's not our, it's for other cores.
So it's just the dual problem.
Yeah, it's by linear duality. Okay, so now we have good news. It turns out that index function is difficult when we take D uniform over all the inputs. It's the only thing we have to prove, and we are done with our big theorem here. Make some space. Well, now we don't need to random strings anymore. And let us look how our problem looks like. So, and then Bob has to tell X. That's our problem. And he has to do it right with probability 2/3 if we pick a random X over the bit strings and a random I for here. Okay, so Bob has this function where he answers using the message and his input I. So now let us think. So what will I do? I will set k equal to c times n. What is c? C is 0.001, small constant.
It's
Yeah, the constant from the theorem. Yeah.
Okay.
I will take here c times n, and here I want to add the c times n as well.
So 3 is 1 over 1,000.
Yeah, that should work. Okay, And so what we assume is that, so we want to prove that C times n, messages of length C times n are not enough. So Alice will send a message C of length most C times n. And now we will prove that Bob will fail with probability more than 2/3. Will fail with probability, with probability more than 1/3. Okay, yeah. That's actually the proof uses 1/4, but you can change it. You can tweak everything, and then so sorry for changing. Now I suddenly remember that we need 1/4. Yeah. At least in the constants that I just read, I'm not sure if I can change everything on the fly. So, okay, but after I explain, I can change the constant to get 1/3, and everyone is happy again. Yes, okay. So now, so what's the idea of the proof? So let us think that Alice can use 0 bits of communication. Yeah. So we know that something, just to make things extreme, it's like if you have no inspiration, you can look to extreme case. And so then Bob doesn't get any message, and he gets a random index, and he has to guess right. And so you can think okay, so Alice has an X, and Bob has to know information about X and has to get the bit. So he will he has a deterministic protocol. So it means that for any X, he will give the same answer always. And so his answer, he will be right. So this probability being wrong, so D is uniform. So his probability will be slightly better, exactly 1/2 of making us. So he will finish. Okay, now imagine that he gets 1 bit of information. Then Bob can do a tiny little bit better than random guessing. For example, he can get the first bit of X, and then he's a little bit better than random guessing. Okay, so imagine he gets 5 bits of information. Then he can do a little bit better. So there is kind of union thing going on. And let us now look. So when we fix the message, then we can feed all eyes to Bob and see what he says. And then we get something called answer string. Let's call it answer string. So there is an A of a message. And this is equal to answer Bob. For 1, so it's a vector. So here the answer string. So Bob answer when he gets the message and its input. So Bob has 2 inputs, the message and I. And he has produced an answer. So let's try all I's, and then we get this answer string here. Yeah. For M is the message, and the second argument is the index.
Yeah, so it's from 1 to M.
Yeah.
I can just.
Yeah. Okay. Let me write it better because it's important information. So that is just both answer of X and I. Now let us define A M.
Is X random?
Yeah.
Or L is
X is uniform and I is also uniform.
okay.
Okay, is it clear what is meant with answer string?
You mean uniformly just distributed on the by strings of length n?
Yeah, yeah.
Okay.
So in this probability, P is uniform over X and Y's. So uniform over n bit strings and number from 1 to n.
So
Yeah, so this is an answer string. And now what do we want if we give so when let us say what are good strings? So we will prove that for a lot of X, both will give poor answers. But there can be a few X where Bob gives good answers. So what do we want to know is that we want that X and A for the message of X, that they have small Hamming distance. They should differ in a few, at most a few bits. Right? So on average, so expected value of this Hamming distance should be at most 1/4. That's what we have to prove. Okay. But now let us look to all the strings. The set of all strings. We know there are only a few messages. So we have only a few answer strings. A1, A2, and the last one is A2 to the power Cn. Because that our upper bound on number of messages is exponential. And so one for X to be a good string, and let's say that it's good if the Hamming distance is Hamming distance of X and A message X, and this let's say for my memory. Sorry, I will prove it for 1/8. Sorry for changing the constant. Okay, but we can deal with the constant later. If the Hamming distance is n/4, is at most n/4, then we are happy because we are doing better than what is expected. And so the average Hamming distance needs to be at most n/8, but let us say that we are already happy with n/4. So let's call this a good X. This means that good X's, they lay not too far from their answer string. So any X that is good, so imagine X is good, then X must be at Hamming distance n/4 from one of the answer strings. It's needed for answers for X to be good. So we say that X is good. X is good, that's our definition. If Hamming distance of X and answer string of X is at most n/4.
yeah, it reminds the proof of common correction codes from algebra.
Yeah, exactly. It's very closely related. Okay. Now I will prove that at most half of the strings X are good. And how will I prove it? I will sum up the sizes of all Hamming vowels. And I will say that it's less than half of all the strings. So here, let me write it. Lemma at most 2 to the power n minus 1 strings in 0, 1, n are good. This is our lemma. I forgot if this is good marker. Yes, excellent. Okay, lemma at most half of the strings in are good, of length n are good. Okay, and now we will just we know there are at most 2 to the power cn Hamming balls, and we need to bound the size of one ball. So to bound the size of a ball, okay, I can delete this. Because after you all agree, after this lemma is proven, we are done. Because what it means that at least half of the strings are bad. And bad means that average error is at least 1/4. So all the bad strings contribute, sorry, more than 1/4. All the bad strings contribute more than 1/4 here, and at least half of them are bad. So it means that if we use this amount, if we use cn bits of communication, then this probability is violated. On the other hand, so if this probability is not violated, we need more than cn bits of communication. And so condition of this theorem is satisfied. So after we get this lemma, we are done. So for this, we just have to remember what's our goal. Expected value of this Hamming distance should be at most 1/8. But we prove that for at least half of them, it is more than n/4. So this error is expected value of Hamming distance. That's connection. And so now I can delete lemma to have some space for calculation. Okay, so now what is size of Hamming ball? X and K. So this is the how many strings are there that differ in K positions from a string X. And this is this exact formula. It is n choose I, and I goes from 1 till K, from 0 till K. And so there exists formula. I will prove it later, otherwise we'll get boring. And the formula is e times n over k to the power k. I will prove it later. Okay. So now let us count the union of all the balls. It is 2 to the power cn times en over k to the power k. So this is the number of good strings. Number of good strings at most this thing. And what is the value of k? Do you remember? Cn.
Where C is
No, I'm lying to you.
N by 4.
Yeah, n by 4. Yeah. So k is n by 4. So in the denominator we have 4e to the power n over e. So this e is 1000. I was messing up. So this is equal to 2 to the power c, and here we have 4n to the power 1/4, and all this to the power n. Okay, and now we sorry, there is no n here, there is e here. 4e. So n over k is 1 divided by 1/4, so we get 4e, and cancels out here. And then we have n over 4 in the exponent, so 1/4 times n. Okay, e times 4 is less than 12. And then we take 4th root, we have something less than 2. And then c should be small enough that the power is still smaller than 2. So this is smaller than 2 to the power 0.99n.
What is the deal of X and K?
What is the Hamming ball? All strings that differ at most k positions from X. So it's a very important thing. So Hamming bar. I can write it in full.
No,
Okay, yeah. So the size of X tilde for which Hamming of X tilde is smaller than K. So, and this for large n. So if n is more than 1,000, then this is smaller than 2 to the power n minus 1. And so the lemma is proven.
and what is K?
N over 4. So K was from the Yao lemma, and we use it with n over 4. Okay, so it means we finished the proof that communication complexity of offset disjointness is linear. And so now it's 17 minutes left. So there is no. Yes. Okay, somebody has internet problems. So there is no chance I can explain both things in 15 minutes. So if you want to learn this, why 1 over epsilon squared is optimal, you will need to read the lecture notes of a rough garden, but the link is on the wiki. So especially the last one, gap Hamming has omega n lower bound. It goes by reduction from index problem, which we just proved. But this reduction is extremely, it's not so big. It's 1 page and a half explanation, but it's very unexpected. So it's simple, but no chance I would invent this if I had to myself. So and it's also nice because it's probabilistic reduction. So it makes only sense for probabilistic versions of the algorithm. So it's another reason why this probabilistic communication complexity is important.
Now we need to choose what we want to hear about.
Oh yeah. So there is free time left, yeah. Because it will be anticlimax if I start to explain like the outlook of the proof, but without details. If you want, I can explain how I prepared the explanation of the full proof, but I was too slow with this proof. I couldn't time the lecture. I was in a hurry, so yeah. If there is some part you found difficult, then
I can find Yao also in the current lecture notes. Yes. Yao theorem.
Yeah, Yao theorem. It's in the lecture. Sorry.
Can I find?
Yeah. You can see it here.
Thank you.
Yeah, that's too far, I guess. It's the beginning of the proof, but yeah, there.
So maybe some life hacks for the colloquium.
Ah.
What to write on the paper sheet allowed to bring?
Yeah, just thing that you find difficult to remember. I mean, it's different for everyone. I would write the IO lemma. I always forget
For example, are we allowed to write on both sides of the sheet?
I don't remember what I wrote. Normally, I say it clearly. So didn't I say it clearly in the rules?
If I'm mistaken, yes. Probably this one is of the.
Yeah. I need to be careful because I remember I was changing my opinion.
You may bring one sheet of paper with the person can read notes on both sides.
Okay, yeah. Yeah, I copy pasted from 3 years ago. I don't remember. Yeah, I didn't think about it. Yeah.
So technically we can write so small.
Yeah. That's why I was thinking about doing it on one side. There was also the first time I did it, there were guys who like printed 24 pages of syllabus on one side and then 24 on the other side, and they didn't need to remember anything. So that's why I say handwritten, because you cannot go so small.
And is it true that every statement which we can find in colloquium, it is in colloquium list?
Yeah, I will take random questions.
So
So,
there is no other questions.
Yeah. So only
Okay.
but I will check whether you understand. So I will read your answer, and if it's precisely the same as I wrote on the board or the thing, it's okay, it's allowed. But then I will think whether you understand it by saying, okay, if X is 5 and if Z is 6.
Even
What-
Vladimir Charjantsev once said me that the access to the internet doesn't help when we discuss the problems and the exams. Okay, we have some access to the material, but if we don't know the material, we cannot pass the exam because if you ask something, I will just not be able to answer the question because I just don't know myself.
Yeah, I understand that if the material is really clever.
No, I mean
but-
that the sheet of paper is not so useful when you don't prepare. So
Yeah.
We anyway have to learn all the.
Yeah, but what happens is that if I don't allow to, if the books are closed, already 1/3 of students will leave half of the question open. I mean, it goes much faster. And also I see immediately if it's something changed with my words or what I remember, what I explained. And that means that you were actually thinking while writing. And then I look at it and I say it's okay. But also I know from the lecture, so if you, like you were asking questions, and so sometimes I remember when I see colloquium, I remember the questions and I say, okay, that's good. Yeah. Yeah, it's a matter, but I think that it's wrong in sense. Like if you can only write a little bit, actually you can keep it if you want.
The question about the format, is it oral or we just give you our works and you check?
Yeah, it's oral, but it's easier if you write the answer and then I check
So
it.
it's like the usual exam.
Yeah,
We discuss everything and
yeah,
after I leave the room, I know my grade, for example.
yeah, and I tell you it's good or not. And so I hope I don't need to check basic knowledge. So because usually it's 25 students, and then 2 or 3 times I have to check basic knowledge, and then everyone has. So if you have half of the score for the question from list 1 and list 2, then I can also not do it.
So we get 2 points for the attendance. 2 points are given us automatically if we get
Yeah.
3 points. So we get either 7 or
Yeah.
4.
So, well, if the basic question is right, then you can, any score is
So
possible.
it's
It's
not-
any score, yeah.
Yeah, it's not possible to get 6 because
No, it is possible. because if you know basic question, so if you have
Okay, if I have
2.5,
okay,
yeah, for out of 6, and then the basic question is right. But I agree. I think it never happened.
6 points for the exam.
Yeah, for colloquium.
So
I have a question. Will the exam for software engineering students be held in this?
Oh, sorry, you didn't know. Yes, yes, yes. Everyone together. And then this part is finished. And then it's new material in January.
Okay.
So the exam will be.
Yeah, it's just a little material because for software engineering, it's even much harder than for other students. Although, no, evaluation said it was easy course. But
So the exam will be organized during the
lecture.
exam week.
Exam, yeah, will be in the exam week. But I need to find this email where they gave the link with the schedule. I cannot find it. But you didn't receive any email.
Oh,
They
no,
didn't tell you anything yet.
no. Can we do the exam online?
If there is reason, only if there is reason.
I need to come to my parents and the texts close to the new year are just too expensive.
Yeah,
we
okay.
come home at the beginning.
Yeah. So I will allow it, but you need to send me an email.
Okay.
Yeah. But yeah, it's
think-
kind of tricky. I mean, I know you were in all the lectures, so I will decide for every person separately. But if you are in the lecture, I will allow it.
For the exam, there is no much difference since we are allowed to use the book. And the exam,
Yeah.
So,
Well, but not internet. So yeah,
okay.
just the books are allowed. So then you need to promise only use the book from the literature and inside.
Do we have different deadline from for extra homework task or no?
For extra task, no, it's too late now. Yeah.
Another question for software engineering students. We only have some classes during the third module.
Yes, I plan to give some classes. Yeah.
So in the course description, it's just about some project.
Yeah, I didn't change it.
I'm not sure, but I didn't know whether the class would be or.
Yeah, actually, part of classes are in LMS too. So if you want, you can. So that's what I did last year. So, but it was a very light task last year.
About the parameterized complexity.
Yeah.
So the last year it was easy to get 0.25 from the.
Yeah, but there were 4 students and only one got 0.25. And the 3 others, if I remember correctly, they even screwed this easy task. But I think I was too lazy last year. So I will give 3 lectures or something like this. And then homework and small programming project. And I will try to make grader in C++. So now it's grader in Python, but it's a bit stupid because it's for time. You have to solve something. I mean, if you think very well, you can solve in Python, but then I will make another time limit for C++. Okay.
On the development will be only you or the Slav and computer also?
Since I've only 10 people submit homework, so I guess there will be at most 15 people. Like there's always like an increase, like by 30% of people who want to just pass with minimal effort.
How many of them usually pass? So the proportion and the grade from the colloquium.
Yeah, but they're surprisingly clever, these people. They just don't care about their mark for certain courses.
But what about an answer on my question? Will it be only you or?
Only me, yes, yeah. Yeah, so sorry, yeah, and because I expect few students, I hope I can handle myself.
Yeah, and it's also 2 dates, so they will divide on 2 dates.
Yeah, and also you can come later during the time of seminar. I will still be here. Yeah, it's not only of time of lecture. Okay, I should make this clear and yeah.
This room for the seminar.
Yes. I think it's this room.
By the end of the course,
Mhm.
so at the beginning of the course, for the homework, we were just excellent, and by the end of the course, the enthusiasm, so many activities, diploma project, and the grades decreased. I didn't. From the last 2 homeworks, I just did only one.
Yeah, I didn't see any grades from last homework.
Yeah.
Yeah, it's not yet. It's not good, but yeah. So yeah, it was a nice group here because only few students, but half kept coming till the end, and it's my explanations are not always so clear because I teach 2 courses, and after one lecture I'm completely tired, and then yeah, I don't know what it is. If I have to speak, I become tired very fast. And also I had to prepare. If I'm late with preparing previous course, then yeah, so it was a bit scary. But I like it because all both courses are in one day. So yeah, it was very good students that are very patient. Yeah. So,
I would say here for the seminar. Well, the personal question. This year I'm applying to some universities. Is it possible to ask you to give some recommendation later?
yeah. But it's not. Yeah. I want to do it. I mean, it's just not. I have students already asked it. The problem is that I only know you from this course.
We just private, you know. From I think. No. So it's okay.
Yeah, I understand. But the problem is that it doesn't help much. So what your thesis supervisor writes will be
my
10 times more important.
So my thesis supervisor is more about management courses, some agile and others. So you're more mathematical and theoretical.
Yeah.
So it will be good balance.
Yeah. That's good. Send me an email and then like if you have inspiration about what else. So I will say that you're communicative in the lecture, helping everyone, warning for confusions and so on. Okay. Yeah.
I'll write if I will need it. I think I will need it.
Yeah.
I will write. Thank you.
Okay. Oh, I was still recording. I will cut